Put two fingers on your wrist right now. Find the pulse. Feel it. That rhythmic push against your fingertips is the pressure wave from your heart slamming shut a valve and forcing blood through a tube that was never designed to carry this much pressure for this many years. You are feeling a system that evolution built for a creature that was supposed to die at 35. You are running it at 55, at 65, at 75. And the physics of what is happening inside those tubes is something no doctor has ever properly explained to you. They give you a number, 120/80, 140/90. They tell you it is too high. They hand you a pill. But they never tell you why the number keeps climbing, what is physically changing inside the walls of your arteries year after year, and why evolution not only failed to prevent it, but actively caused it. I spent my life studying how organisms are shaped by the forces they face. Every beak, every claw, every bone in every creature I examined on the Beagle voyage told the same story. The body is not designed for comfort. It is not designed for longevity. It is designed for one thing only: reproductive success in the environment the species evolved in. And the environment your cardiovascular system evolved in looked nothing like the one you are living in now. The pressure problem. Let me explain what blood pressure actually is, because the number your doctor gives you obscures the physics. Blood pressure is the force per unit area exerted by your blood against the interior walls of your arteries. It is measured in millimeters of mercury, an old unit from the days when pressure was measured by how high it could push a column of liquid mercury in a glass tube. 120 millimeters of mercury means the pressure inside your artery at the moment your heart contracts is sufficient to support a column of mercury 120 millimeters tall. That is a meaningful amount of force applied to a tube made of living tissue. There are two numbers because the pressure oscillates. Systolic pressure, the top number, is the peak force during a heartbeat, the moment the left ventricle contracts and shoves blood into the aorta. Diastolic pressure, the bottom number, is the residual force between beats, the pressure that remains in the system while the heart is refilling. You need both. Without systolic pressure, blood would not move. Without diastolic pressure, blood would stop flowing the instant the heart paused between beats, and your organs would starve during every fraction of a second of cardiac rest. Now here is what I want you to understand. This system, this pulsatile pump driving fluid through elastic tubes, has been operating continuously since before you were born. Your heart began beating roughly 22 days after conception. It has not stopped once. Not for a single beat. By the time you're 70 years old, your heart has contracted approximately 2.5 billion times. No mechanical pump ever built by human hands has operated for 2.5 billion cycles without maintenance, without replacement parts, without a single shutdown for repair. Your heart does this while you sleep, while you eat, while you argue with your children, while you forget it exists entirely for weeks at a time. But the heart is not where the problem lives. The heart is a pump. It generates pressure. The problem is in the pipes. Why your arteries are hardening right now. The aorta, the largest artery in your body, exits the top of your heart and arches downward through your chest. It is roughly the diameter of a garden hose. And when you are young, it is elastic, genuinely elastic, like a rubber tube. When the heart contracts and forces blood into the aortic wall stretches outward. It expands. It absorbs the pressure pulse like a balloon absorbing a sudden burst of air. Then, between heartbeats, the wall recoils. It springs back to its original diameter, and as it does, it pushes the blood forward, maintaining flow during the pause between beats. This is called the Wind-Kessel effect, and it is one of the most elegant pieces of engineering in the human body. The aorta converts the pulsatile output of the heart, which comes in sharp bursts, into smoother continuous flow through the smaller vessels downstream. Without this elastic buffering, every heartbeat would send a shockwave through your circulatory system. The pressure peaks would be dramatically higher, the pressure troughs would be dramatically lower. Your organs would be hammered with each systole, and starved with each diastole. The elastic aorta smooths the pulse. It is a shock absorber made of protein. The elasticity comes from a protein called elastin. Elastin fibers are woven through the walls of your large arteries in concentric sheets, layered like the rings of an onion. Each fiber can stretch to roughly 150% of its resting length and snap back without damage. This is an extraordinary material property. Most biological proteins cannot do this. Collagen, the other major structural protein in your artery walls, is stiff. It resists stretching. It provides strength. Elastin provides give. The two work together. Elastin handles the normal range of pressure variation. Collagen acts as a safety net, preventing the wall from stretching too far under extreme pressure. Here is the problem. Elastin is manufactured almost entirely during fetal development and early childhood. By the time you are a teenager, your body has essentially stopped making new elastin. The elastin fibers in your aorta right now are the same fibers that were laid down before you were born. They are as old as you are. They have been stretching and recoiling with every single heartbeat for your entire life. 2.5 billion cycles of mechanical loading on protein fibers that cannot be replaced. Think about any elastic material you have ever used. A rubber band, a bungee cord, the elastic waistband on an old pair of shorts. What happens to elastic material over time, over millions of stretch and recoil cycles? It loses its elasticity. It fatigues. The molecular crosslinks that allow the protein to spring back begin to fracture. The fibers fragment. They calcify. Calcium deposits form along the broken fibers, turning soft, elastic tissue into something approaching the stiffness of calcium mineral. Your arteries are literally becoming harder. This is arteriosclerosis. Not atherosclerosis, which is the accumulation of fatty plaques inside the artery. Arteriosclerosis is the hardening of the artery wall itself. The structural degradation of the elastic material that was supposed to absorb the pressure pulse from your heart. As the aorta stiffens, the Wind-Kessel effect degrades. The wall no longer stretches to absorb the systolic pulse. Instead, the full force of each heartbeat is transmitted directly into the blood column. Systolic pressure rises. This is why the top number on your blood pressure reading climbs with age, even if you are healthy, even if you exercise, even if you eat well, even if you do everything right. The elastic buffer is wearing out, and nothing in your biology can rebuild it. And it gets worse. In a young elastic aorta, the pressure wave generated by each heartbeat travels relatively slowly through the stretchy wall. It propagates outward, reflects off branch points in the arterial tree, and returns to the heart during diastole, actually helping to push blood into the coronary arteries that feed the heart muscle itself. The timing works beautifully. The reflected wave arrives during the relaxation phase and boosts coronary perfusion. In a stiff aorta, the pressure wave travels faster, much faster. So fast that the reflected wave arrives back at the heart during systole, not diastole. Instead of helping the heart during its rest phase, the reflected wave adds to the peak pressure during contraction. It augments the systolic load. The heart is now fighting against its own reflected pressure wave. This is called augmented systolic pressure, and it is a direct mechanical consequence of arterial stiffness. The physics is the same as a wave bouncing off a hard wall versus a soft wall. A soft wall absorbs. A hard wall reflects with force. Why evolution did this to you? Now here is where my work becomes relevant. Why would natural selection produce a cardiovascular system with a critical component that cannot be replaced and is guaranteed to degrade with time? Why would the body manufacture all of its elastin early in life and then stop? Why not continue producing elastin throughout adulthood to maintain the arterial walls? The answer is the same answer I found in every species I studied. Evolution does not optimize for longevity. It optimizes for reproductive success. And reproductive success in our ancestral environment The African savanna, roughly 200,000 years ago, required surviving to reproductive age, mating, raising offspring to independence, and then, from evolution's perspective, you were done. The selection pressure on your genes dropped dramatically once your reproductive contribution was complete. Life expectancy for early Homo sapiens was roughly 30 to 35 years. Not because everyone died at 35. Infant mortality was extreme. Predation, infection, injury, starvation, these killed the majority before they ever reached old age. But the relevant number for natural selection is not maximum lifespan. It is the age range during which your genes are being passed on and your offspring need you alive. That range was approximately 15 to 35.
I saw this principle everywhere during my voyage on the Beagle. In the Galapagos, the marine iguanas that dove deepest for algae reproduced the most. Their bodies were optimized for diving, not for living long after their reproductive years. The giant tortoises, which can live over 100 years, are the exception that proves the rule. They survive because their environment has almost no predators, and their slow metabolism and massive size mean the physics of wear operates on a different timescale. Your ancestors had predators. Your ancestors had infections. Your ancestors had violence. They did not get the tortoise's luxury of time, and their arteries reflect that. Your elastin was built to last that long. 35 years of heartbeats is roughly 1.3 billion cycles. Your elastin can handle that. It maintains its elasticity beautifully through the reproductive window. The degradation begins to become significant somewhere around 40 to 50, well past the age at which natural selection had any reason to maintain the system. There was no evolutionary pressure to build elastin that lasted 80 years, because almost no one lived to 80. The genes that would code for longer-lasting elastin, even if they existed, conferred no reproductive advantage. They were never selected for. They never spread through the population. This is not a flaw in evolution. This is evolution working exactly as it does. It built you to reproduce, not to persist. Your arteries are hardening because evolution built them to a specification, and you have exceeded that specification by decades. The salt paradox. But arterial stiffness is only half of the mechanism driving your blood pressure upward. The other half involves your kidneys, and this is where the evolutionary mismatch becomes truly striking. Your kidneys filter approximately 180 liters of fluid from your blood every single day. They then reabsorb roughly 99% of that fluid, returning it to your bloodstream along with the sodium, potassium, water, and other molecules your body needs. The remaining 1% becomes urine. This system regulates the total volume of fluid in your circulatory system. More fluid means more pressure. Less fluid means less pressure. Your kidneys control blood pressure by controlling how much water and sodium they retain. Now, sodium is the critical molecule here. Sodium is an osmotic agent. Where sodium goes, water follows. If your kidneys retain more sodium, they retain more water. Blood volume increases. Pressure increases. If your kidneys excrete more sodium, water follows it out. Blood volume decreases. Pressure decreases. In our ancestral environment, sodium was scarce. Extraordinarily scarce. The human body evolved on a diet containing roughly 500 to 1,000 milligrams of sodium per day. There was no salt on the savanna, no salt in wild game, no salt in tubers and roots and foraged plants. Sodium was so rare and so biologically critical that your kidneys evolved to be sodium retention machines. They are spectacularly efficient at recapturing every molecule of sodium that passes through the filtration system and returning it to your blood. The hormone, aldosterone, drives this process, and your body is exquisitely sensitive to it. Even a small drop in blood sodium triggers aldosterone release, which tells your kidneys to hold on to every sodium molecule they can find. This made perfect sense 200,000 years ago. Sodium was hard to get. Losing it in urine was wasteful. A body that conserved sodium survived longer and reproduced more successfully. Natural selection favored aggressive sodium retention. Now consider your current environment.
The average person living in the modern world consumes between 3,000 and 5,000 milligrams of sodium per day. Some people consume over 6,000. That is 5 to 10 times more sodium than your kidneys were designed to process. And your kidneys are still running the ancient software. They are still retaining sodium as aggressively as they did when sodium was scarce. But sodium is no longer scarce. It is in your bread, it is in your cheese, it is in your soup and your sauces and your processed food and your restaurant meals. It is everywhere. Your kidneys retain this excess sodium. Water follows the sodium. Blood volume expands. Pressure rises. And the mechanisms that should correct this, the feedback loops that should tell your kidneys to excrete the excess, they work. But they work slowly. They were calibrated for a world where daily sodium intake fluctuated between 500 and 1,000 milligrams. They were not calibrated for a world where you consume 4,000 milligrams at dinner and another 2,000 at breakfast. Over years, over decades of chronic sodium excess, the system drifts. The set point for sodium retention shifts upward. The kidneys begin to treat the elevated sodium level as normal. The blood volume stays expanded. The pressure stays elevated, and your hardening arteries, which can no longer absorb the excess pressure through elastic expansion, transmit the full force to your organs. What the pressure is doing to you right now. Here is what elevated pressure does to the interior of a blood vessel. The endothelium, the single layer of cells lining every artery and vein in your body, is subject to two forces: pressure, which pushes outward against the wall, and shear stress, which drags along the surface in the direction of blood flow. Under normal conditions, these forces are balanced. The endothelial cells are aligned in the direction of flow, streamlined, healthy, producing nitric oxide, a molecule that keeps the vessel wall relaxed and smooth. Under chronically elevated pressure, the endothelium is damaged. The cells are distorted. The production of nitric oxide decreases. The wall becomes stickier. White blood cells begin to adhere to the damaged endothelium. Low-density lipoproteins, the particles carrying cholesterol through your blood, penetrate through the damaged lining into the wall itself. They accumulate. They oxidize. The immune cells that follow them in try to clean them up by engulfing them, and in doing so they become foam cells, bloated with lipid, dying inside your artery wall, forming the core of what will become an atherosclerotic plaque. This is where arteriosclerosis and atherosclerosis converge. The stiffening of the wall creates the mechanical conditions for elevated pressure. The elevated pressure creates the biological conditions for plaque formation. One feeds the other. And both accelerate after 50 because that is when elastin degradation crosses the threshold where the Windkessel effect can no longer compensate, and the full force of each heartbeat is delivered unfiltered to every vessel wall in your body. The vessels most vulnerable are the ones where flow is turbulent, at branch points, at curves, at the bifurcation of the carotid arteries in your neck, at the openings of the coronary arteries feeding your heart. These are the places where shear stress patterns are disturbed, where the endothelium is already under mechanical stress even at normal pressures. Elevated pressure at these sites accelerates everything. The damage accumulates faster, the plaques grow larger, the vessel narrows, and your heart, which has been pumping against increasing resistance for years, does what any muscle does when forced to work harder. It grows. The left ventricle, the main pumping chamber, thickens its wall to generate more force. This is left ventricular hypertrophy. It sounds like an adaptation, and in the short term it is. But a thicker heart wall is also a stiffer heart wall. It does not relax as easily between beats. It does not fill with blood as efficiently. Over time, the heart that grew stronger to overcome the resistance becomes the heart that cannot relax enough to fill properly. The pump that adapted to the pressure becomes a victim of its own adaptation. I observed something across every species I studied during my years of fieldwork. The most dangerous threats are the ones the organism cannot detect. A predator that moves silently is more lethal than one that roars. A poison that has no taste kills more reliably than one that burns the tongue. Natural selection sharpens the senses against threats that can be perceived. It has no mechanism for threats that are invisible. Elevated blood pressure has no symptoms. None. You cannot feel it. Your arteries have no pain receptors on their interior surfaces. The endothelial damage, the plaque formation, the ventricular hypertrophy, all of it proceeds in absolute silence. You feel fine. You feel completely normal. And inside your arterial walls, the physics of pressure and stiffness and turbulence and inflammation is remodeling your cardiovascular system day by day. This is why it is called the silent killer, and the name is precisely accurate. It kills by being undetectable to the organism it is destroying. And this makes perfect evolutionary sense. There was never any selective pressure to develop the ability to sense blood pressure, because blood pressure was never a problem during the reproductive years. It rises after reproduction. It causes damage after reproduction. Natural selection cannot see it because natural selection is functionally blind to anything that happens after you have passed your genes to the next generation. I spent 20 years writing On the Origin of Species. I spent decades building the argument that every feature of every organism is the product of selection pressures acting over immense time. And the rising blood pressure in your arteries right now is one of the clearest confirmations of that principle I could ever point to. Your body is not failing. Your body is performing exactly as it was selected to perform. It was selected for a world where you would be dead by now. And the fact that you are not dead, the fact that you are alive at 55 or 65 or 75, means you are running a system past its evolutionary warranty, and the physics of that system is catching up with you in exactly the way the physics of any system catches up when you exceed its design parameters. What you feel under your fingers. Put your fingers back on your wrist. Feel the pulse again. What you are feeling is a pressure wave generated by a pump that has been running for decades without stopping. That wave is travelling through arteries that are stiffer than they were 10 years ago, and the stiffness is increasing with every passing year because the elastic protein in the walls was manufactured before you were born and has been mechanically loaded 2.5 billion times without replacement. The fluid carrying that wave contains more sodium than your kidneys were designed to handle, and the excess volume is adding hydraulic force to a system that can no longer absorb it. The lining of those arteries is under mechanical stress that is quietly causing damage you cannot feel. Damage that will not announce itself until a vessel narrows enough to starve an organ, or a plaque ruptures and blocks flow entirely. This is not a disease. This is physics operating on biology that was built to a specification you have outlived. The specification was 35 years. You're asking for 80. And the difference between those two numbers is written in the stiffness of your arteries, the thickness of your heart wall, and the number on the blood pressure cuff that keeps climbing no matter what you do. I studied finches and tortoises and barnacles and worms. I studied how every living thing is shaped by the forces acting upon it over time. And your cardiovascular system is shaped by a force that stopped acting on it 200,000 years ago. The force of natural selection, which built it for a short, brutal life on an African plain and then abandoned it to run in a world of salt and sofas and 80-year lifespans it was never meant to sustain. Feel the pulse. It is still there. It is still beating. And the fact that it is still beating, after all those billions of cycles, through all those decades of mounting pressure, in a body that has outlived everything evolution prepared it for, that is not a medical problem. That is the most remarkable thing your body does. It keeps going. It keeps pushing blood through hardening tubes with a thickening pump, running ancient software in a modern world, doing its best with a design that was never meant to last this long. And it is still working, right now, under your fingers. Feel it.
That is your inheritance from 1,000,000 years of survival. Use it while the physics still allows.